In this short video, we will discuss what properties are used to describe the nature of solutions, and how to quantify the concentration of a solution. Remember that solutions are homogeneous mixtures that may be solid, liquid, or gaseous. The properties of a solvent determine whether a solute will dissolve. How quickly a solute dissolves depends on how the solute particles interact with the solvent particles. What happens when you add sugar to tea? Sugar dissolves faster when you stir the tea or when the tea is hot. Granulates sugar dissolves faster than sugar cubes do. The following factors determine how quickly a solid solute dissolves. Agitation. Stirring or shaking speeds up the solvation process, because water in the tea interacts more with the surface of the sugar. Temperature. Water molecules move faster at high temperatures, so water molecules will collide with the surfaces of the sugar crystals more often and with more force. Particle size of the solute. Smaller particles in the granulated sugar have a larger surface area than the sugar cube. Water molecules collide with more molecules in granulated sugar. There is a limit to the amount of solute that can be dissolved in a solvent. This is the solubility, which is defined as the amount of solute that can dissolve in a given amount of solvent. If we dissolve 10 grams of salt in 100 grams of water at 25 degrees Celsius, we have created an unsaturated solution. An unsaturated solution is a solution that can contain more solute. 36.2 grams of salt is the maximum amount that can be dissolved in 100 grams of water at 25 degrees Celsius. This is a saturated solution, or in other words, a solution that cannot contain any more solute. If you add more solute to a saturated solution, it will not dissolve. In a saturated solution, an equilibrium exists between the solution and the undissolved solute at the given conditions. The beaker contains a saturated solution and an undissolved solid. Particles move back and forth from solution to solid at the same rate, so the total amount of dissolved solute remains constant. Some liquids are completely soluble in each other. These are called miscible liquids. Example: any amount of ethanol will dissolve in any amount of water. Liquids that are slightly soluble in each other are partially miscible. And immiscible liquids are liquids that are insoluble in each other. Example: oil and water. Let's discuss what factors affect the solubility. From the graph, we notice that temperature will affect the solubility. The solubility of most solid substances increases as the temperature of the solvent increases. Here the solvent is water. The solubility of some substances decreases as the temperature increases. Ytterbium sulfate is an example. The solubility of other substances changes very little with temperature. Example: sodium chloride. The solubility of sodium acetate in water is greater at 30 degrees Celsius than at 25 degrees Celsius. Make a saturated solution of sodium acetate at 30 degrees Celsius, and let the solution cool to 25 degrees Celsius. If no crystals form at 25 degrees Celsius, then you have made a supersaturated solution. A supersaturated solution is a solution that contains more solute than a saturated solution. By adding a tiny crystal of solute, called a seed crystal, solid crystals quickly form from excess solute. Now let's discuss the solubility of gases. Temperature and pressure affect the solubility of gaseous solutes. The solubility of most gases decreases as the temperature of the solvent increases. Example: as the water temperature increases, the solubility of oxygen in water decreases. Changes in pressure have little effect on the solubility of solids and liquids. But pressure has a big effect on the solubility of gases. Henry's law describes these effects. Henry's law explains that the solubility of a gas in a liquid is proportional to the pressure of the gas above the liquid. You can see the principles of Henry's law in action when you open a carbonated beverage. Large amounts of carbon dioxide are forced into carbonated drinks under pressure when they are bottled. When you open a bottle, the pressure of carbon dioxide decreases, and bubbles of carbon dioxide form in the liquid and escape from the open bottle. Once the bottle is open, the concentration of dissolved carbon dioxide decreases. How can we describe the concentration of a solution? Concentration is the amount of solute dissolved in a certain amount of solvent. The most important unit of concentration is molarity. Molarity is the number of moles of solute dissolved in 1 liter of solution. Note that the volume involved is the total volume of the solution, which is equal to the volume of the solute and the volume of the solvent. The formulas shown allow to calculate the molarity if the moles of solute is known, or the moles of solute if the molarity is known. To make a 0.5 molar solution, first measure the mass equivalent with 0.5 moles of solute. Add 0.5 moles of solute to a 1 liter volumetric flask that is half filled with water. Swirl the flask carefully to dissolve the solute. Add solvent to the 1 liter mark. A dilute solution is a solution that contains a small amount of solute. A concentrated solution is a solution that contains a large amount of solute. A dilution can be prepared by adding solvent to the concentrated solution. Diluting changes both the volume and the molarity of the solution, but the number of moles of solute will not change, as shown in this equation. You can also express the concentration if you know the volume, or mass of the solvent and solute. The first equation shows how to calculate the percent by volume of a solution. The second equation shows how to calculate the percent by mass of a solution. If the solute is a solid, the percent by mass is an easy way to make the solution, by measuring the mass of the solute and mass of the solution. In this section, colligative properties of solutions will be discussed. A colligative property is a property of solutions that depends only on the number of solute particles, and not on the chemical identity of the solute. A solution that contains a non-volatile solute always has a lower vapor pressure than the pure solvent. Remember that vapor pressure is the pressure exerted by a vapor above its liquid in a closed system. Solute particles reduce the number of solvent particles that are able to escape the liquid. With fewer vapor particles, the vapor pressure is lower. The decrease in a solution's vapor pressure is proportional to the number of solute particles in solution. Ionic solutes have greater effects on vapor pressure than molecular solutes do, because they produce more particles in solution. First case, molecular solutes in solution, for example glucose dissolved in water. Glucose does not dissociate in water, so 3 moles of glucose dissolved in water produce 3 moles of particles. Second case, ionic solutes in solution, for example, sodium chloride dissolved in water. Each formula unit of sodium chloride dissociates into 2 ions, so 3 moles of sodium chloride dissolved in water produce 6 moles of particles. Third case, ionic solutes in solution, for example calcium chloride. Each formula unit of calcium chloride dissociates into 3 ions, so 3 moles of calcium chloride dissolved in water produce 9 moles of particles. Boiling point elevation is defined as the temperature difference between the boiling point of the solution and the boiling point of the pure solvent. As we have seen before, adding a non-volatile solute to a liquid solvent decreases the vapor pressure of the solvent. Consequently, more kinetic energy must be added to raise the vapor pressure of the solution to atmospheric pressure, so the boiling point will be elevated. The freezing point depression is defined as the temperature difference between the freezing point of solution and the freezing point of the pure solvent. The particles in a solid form an orderly pattern when a substance freezes. The presence of a solute in water makes it more difficult for the water particles to form this pattern. More kinetic energy must be taken out of a solution before it freezes. As a result, the freezing point of a solution is lower than the freezing point of the pure solvent. Let's discuss calculations involving colligative properties. Recall that colligative properties of solutions depend on the number of solute particles dissolved in a given amount of solvent. Chemists use 2 ways to express the ratio of solute particles to the amount of solvent, molality, and mole fraction. Molality is the number of moles of solute per kilogram of solvent. Mole fraction is the ratio of the moles of solute to the total moles of solvent and solute. Mole fraction has no units. Assume that A refers to the solute and B refers to the solvent. The mole fraction of the solute and the mole fraction of the solvent can be calculated using the formulas shown. Note that the sum of the mole fractions of the solute and solvent is equal to 1. Freezing point depression and boiling point elevation are directly proportional to molar concentration, as shown in these two equations. For ionic solutions, the effective molality has to be used. The table shows the molar freezing point depression constant and the molar boiling elevation constant for some common solvents. A sample problem will be used to show how to calculate the freezing point depression and boiling point elevation for ionic solutions. Here is a sample problem to calculate the freezing point depression for a molecular solution. Given the mass of solute, 100 grams of ethylene glycol, C2H6O2, with a molar mass of 62 grams per mole. Given the mass of solvent, 0.5 kilograms of water, with a molar freezing point depression constant equal to 1.86. First step, convert mass of solute to moles. 100 grams ethylene glycol is equal to 1.61 moles of ethylene glycol. Second step, calculate the molality of the solution. Moles of solute, divided by kilograms of solvent, is equal to 3.22 moles of ethylene glycol per kilogram of water. Third step, now the freezing point depression can be calculated. Here is a sample problem to calculate the boiling point elevation for an ionic solution, in this case sodium chloride in water. Given are the solution molality and the molar boiling point elevation constant for water. First, we have to determine how many particles are produced per formula unit when sodium chloride is dissolved in water. Since the colligative properties depend on the number of solute particles, we need to calculate the effective molality. The effective molality is equal to the number of particles times the solution molality. Now the boiling point elevation can be calculated.